Okay, we'll get started. So, okay, welcome everyone today to our final in our three webinars as part of reviews of the ARCHER2 image competition from the end of last year. Today is our lightning round. So we've got three speakers who are going to talk on three different topics to kind of showcase some of the work they've done visualizing their science and talk a little bit about the science behind what the visuals show. So to start with, I've got Dr. Lucy Bresciano from the NOC, who's going to talk to us about modeling surface waves on ARCHER2. Take it away.
Okay, thanks. I'm glad I got this finally working. So yeah, I'm Lucy Bresciano. I work at the UK's National Oceanography Centre. I'm based in Liverpool. I'm a coastal oceanographer. I do a bit of HPC to do wave modelling. I also look at climate impacts on the coastal seas and impacts on other fields. So I'm going to show you why we're doing the wave modelling, the kind of outputs that I look at every day, explain why we need to do it on a big supercomputer. So I want to try and explain that the waves are important for a lot of things. They're not just sort of charismatic things when you're at the beach. The ocean waves are driven by these local or remote storm winds, but they're really important for, coastal erosion. Flooding is one thing, sea safety, surfers. When you're designing big ships that need to be out with 50-year life expectancies, they need to know what the wave climate is going to be. So there's safety concerns, people working at sea, oil rigs, renewables, all of those things need to have a good idea of the sea state. They can also affect other aspects of oceanography that you might be surprising. So they act as very important mixing, so they can affect the temperature of the sea surface, facilitating that ocean atmosphere exchange. But that can then knock onto other processes. So they can actually alter primary productivity in seas by changing the timing of the spring bloom. They mix down those nutrient-rich waters, and they also mix the oxygen down from the atmosphere. So they do gas exchange, mixing, control of productivity. There's also ice and wave interaction, so they can break up ice sheets and sort of facilitate that summer ice clearance in the polar seas. And they can actually be felt right down to the seabed. So if you've got energetic, long period, these large swell waves, they can be felt down at the seabed, and they can mobilize sediment, and that can be important for offshore infrastructure, seabed habitats. So there's all sorts of stuff that the waves are kind of controlling. So the reason that I'm talking today is because of one of the images that got onto the ARCHER calendar, and it's a map of global sea surface waves. So this is the movie, and what it's showing here is how wind-driven waves move across the ocean. So they're growing along the sea surface. So these hot colours, the red colours, show high waves, and cold blue and white colours are calm areas. So what you're seeing is under these red hot spots, essentially large storms moving across the ocean. So waves grow where the wind's the strongest, and then as that storm tracks across, the waves grow, generating these long swells. So the short, choppy wind seas upscale into these big, smooth swells. So if you imagine sitting on the beach in Hawaii, you get these long, slow waves coming across. And those sort of distant swell waves just keep moving completely unchecked until they hit some land at the other side. So you might have a local storm. I hope you can see my mouse. On the eastern seaboard, and then just moves all the way across and hits the North Atlantic and hits the UK coasts. So as the Earth rotates eastwards, the prevailing winds blow from west to east, and these storms move across, and the waves move across with them. So the trade winds that are sort of that permanent east to west prevailing wind, and then you get these storms that are tracking up in the sort of the extratropics, where you get these largest storms moving across. Whereas close to the tropics, the intertropical convergence zone, that's known as the doldrums, it's the windless waters where the boats just can't get moving. So you get these really, really low sort of cold colours here because there's just hardly any wave energy. You also see round the bottom, so around the Antarctic, there's no land to get in the way. So you can actually build some really large storms up here without the wave energy getting hit at the coast or dissipating at the seabed. So that's the kind of result that I would look at every day. And wave modelling is relatively easy based on what forcing you need. So you only need three sort of forcing terms to do a wave model. You need to know what the winds are doing, because that's what's imparting the energy. You also need to know the bathymetry, so the water depth, and then you also need to know the sea ice cover. So if you've got an area, got the wind blowing over the ocean, great, it can impart some energy, build up those waves. If it's got partial or solid ice surface, there's no energy going in, The partially mixed ice is quite interesting because you kind of, if you've got some floating ice, you are going to be able to get a momentum transport from that atmosphere to ocean, but it's kind of dissipated by moving the ice around. And then you need to know what the water depth is, because as these waves, as these long waves move into shallow water, they start to, they call it feeling the bottom. So these circular, these orbital motions start flattening down into sort of ellipses until at the bottom you just get a back and forth motion of that energy. And that's where that sediment transport comes in, that you can get that seabed disturbance from what seems like quite a distant storm can actually be hitting the seabed. So those are the only four things we need: wind, ice and seabed. But it's not as easy as all that, because when we do compare it with something like hydrodynamic modelling of just the ocean, we only sort of carry around the velocity and the water level in that. So you only have like UVW, so three current vectors, and then the water level, maybe some tracers, a bit of physics, a bit of biology. When you do waves, you are actually carrying around a whole spectra of energy. So we don't like represent single wave crests coming back. We represent the wave climate as a spectrum. So how much energy is it at those different wavelengths? So you imagine the short waves are these short, choppy, little wind-driven waves, and then the large swell waves have long periods. So you can have a lot of energy in these long period waves. So actually, at every gridded point in the numerical model of the globe, we are carrying around the amount of energy associated with which each one of those frequency spectra, and then they're also moving in a direction. So this is a 2D directional spectra. So your coordinates, if you like, are actually x and y, and frequency and direction, and then you have the energy associated with that, and that spectra is actually what you move around the global ocean. So it becomes a bit heavy, and it becomes carrying around a lot of extra variables that need to know about each other. So you have, and you can improve your resolution. So like you would zoom in with higher resolution in space, you can also improve your frequency resolution in that energy density space. So it just makes it a bit harder. In this case, I was only using an atmosphere and wave model, but we also did a couple modeling. So if you want to make it harder, you can couple your hydrodynamics and wave together, and then you get a lot more interaction. So rather than just blowing your wind over, generating some waves, you can have feedbacks with the surface current. So you might get behaviors. The waves might act in the same direction as the current, and that can accelerate everything. They might act against themselves, and you get some choppy waves, more stirring. If you just have no wave model, an ocean atmosphere model on its own, they kind of just ignore the waves and they're parameterized away, just make an assumption about how much mixing there is going on. But if you add this coupling in, you can get some more non-linear reactions. The importance of the seabed becomes more important. So you've got this shallow water areas. You can imagine if the tide is moving in and you're really shallow water, those waves can approach the coast on a high tide. The water's going to be a lot deeper, or on a low tide, and then the waves feel the bottom sooner. So you can get quite a lot of non-linear interactions if you start coupling the waves and currents together. And the reason we're doing these global wave models is actually to look at very long-term trends, because there's an indication that under climate change and the climate crisis, that the sea state and the waves are changing. So we're seeing generally there's kind of a stilling over the North Atlantic. Things are getting calmer, but when we get storms, they're becoming more intense. So there's this question of what does that mean for the sea state? So actually we're seeing this trend in the frequency of these very high wave events, these rough days, is kind of going up. And this is important for you if you've got your flood, if you've got your extreme conditions. It doesn't matter that the calmer days are getting a little bit calmer. Really, you want to know about how these extremes are changing. So there's been some work done on long decadal simulations of these wave models, and then looking at trends into the future. So we're seeing whether or not the likelihood of these extreme days are changing. And that's depending really on what the storms are doing out in the North Atlantic, for example. But the waves are also sensitive to that sea ice that I mentioned. So if you think about the winter and summer sea ice, just the winter on the left and summer on the right, if you think about the Arctic, that's the seasonal contraction goes away. So you've got this new ice-free area where the winds can impart energy to the waves. So you end up growing large waves where there weren't any in the winter. So even though better weather, calmer, you're not getting so many storms, you can actually see areas where the wave height increases over that summer because of the sea ice retreat. So it's quite a complicated climate picture, and we have to run a bunch of model ensembles. The wave model can be just downscaled to higher resolution to get coastal impacts. We can run a bunch of future climate projections under different levels of carbon emissions to see how sensitive the waves are going to be. And it is a complicated picture, but generally we see this reducing sea ice is a really clear signal because of the rapid warming that we're already committed to, rapid sea level rise. And if you have combined that sea level rise with changing storminess, you can change the amount of wave energy that gets to the coast, and that can be important for flooding. If we get the warmer ocean temperatures, that can give more energy to these storms. So the storms and tropical cyclones are likely to become more intense, greater rainfall, higher winds, and that can bring some large waves as well. Whereas the polar latitudes are heating, so actually that's making things sort of still down in the background, this global ceiling. So on average, the low lows are kind of dropping off and the waves are less energetic, but when they come, these storms can be really quite intense. So that's all I wanted to show today. Just the fact that we have to run these seemingly straightforward models. You have to have a big compute cost behind them, and because there's a lot of uncertainties, we end up sampling a lot of space. So we can do that by exploring intermodal variability, run decadal simulations to understand what amount of this is coming from natural variability, what's the model uncertainty, what's the climate uncertainty, and then we can look at trends that might be important for things like rough days, which are important for sea safety, coastal erosion, and flooding. Okay, thanks a lot.
Thank you very much for a very interesting talk. Before I have a couple of questions. Before I jump in, are there any questions from the audience? Just post them in the chat if you have anything pressing. Okay. So one question I had is, you may have mentioned this, but I'm not sure I fully picked up. The GIF, the little video you had, what were the sort of timescales you're modeling there within that simulation?
Yeah, so I think that was only a couple of months. I'm not sure what it was. I think there was like maybe there was a slide every hour, because these storms move quite fast. If you think of sitting in the UK, actually we're quite exposed to short, fast-moving storms that might track across in a number of days. So it's really important that when we capture this in the wave model, we have high-resolution forcing, like high-frequency forcing. Because if you have, in the old days, it might be you had a wind every 6 hours. You could almost miss the passage of the storm in that time, so you can't do it. We've done some sensitivity experiments, and actually you can get 3 hourly is okay. Hourly wind is better to be able to get the hit, like the storm time, right? So yeah, whereas if you look at like the mid-latitude, sort of the equatorial zone, everything's much slower, more sluggish. So it's to do with that the Earth's rotation. So up to the polar seas, the length scales are smaller, everything's faster, whereas down at the poles you get these big slow-moving monsoon systems that are kind of easier to model in a way. So actually the bits where we've got the highest uncertainty are those fast-moving small storms where you need high resolution, high frequency, more compute efforts to get it right.
Fantastic. Thank you very much for a lovely talk. We'll move on now in the interest of time, but thank you for joining us. Eric, are you able to share your slides?
Yep. Let me just click on that.
Okay.
Yeah.
I can see them. Fantastic. So Eric's joining us from the Department of Geosciences here at the University of Edinburgh. Take it away.
Thank you. Thank you everyone for joining and this opportunity to share my research on volcanoes. So what you see here in this picture is essentially one eruption that happened in Chile in 2015. What is depicted with this quite beautiful coloring as the sun is setting on this ash cloud is really a volcanic column, which would be hot gas and rocks from microns to meters being transported within this hot plume. I'll discuss some of that that eventually led me to some of the simulations that made it to the calendar. So just a background, volcanoes can produce a variety of processes, some like the volcanic plume and umbrella ash cloud. We call it this way because of the shape that disperses gases in the atmosphere and ash. When the magma is much less viscous, it produces lava flows and lava fountaining. On the other hand, when it's very viscous, you can fragment it brittly and you form a lot of ash and fragments of all sorts of sizes. And what I'll discuss today is that partitioning of the gas and the solid phases, upward and downward. So essentially, you have this dispersed phase erupted, which would be gas, mostly water vapor, with some particles within. Rapidly, the mixture, which can be erupted at temperatures of over 1,000 degrees, is entraining air and starts to cool, and also can, in some cases, become buoyant, right? Where buoyancy in the convective phase starts driving the flow. It very rapidly entrains due to turbulence. As you can imagine, we're talking about Reynolds number on the order of 10 to the power 6 to 10 to the power 10 almost for some of these largest events. Eventually, the mixture cools down and dilutes through entrainment, and there's also a lot of settling happening, and that's what we call the tephra fallout that can have impact on the ground and also for aviation. But eventually, that mixture becomes neutrally buoyant and starts spreading in the umbrella ash cloud. So here I just remind you of some things that I mentioned. Temperature can be wide from what we call a low temperature magma is 1,000 Kelvin, and high temperature would be about 1,300s. The initial velocities are really, really high, so you have high Reynolds number, and therefore it's a flow that is extremely turbulent. It transports grain size that are so variable that the fluid phase and the particle coupling is very complex, and it ranges from really one-way coupling to all the way to four-way coupling, as well as even stuff like that is so coarse that it doesn't get really well coupled with the columns and travels as ballistics. Some of the largest observed flows we've seen go up to 50 kilometers or plus. One of these recent events happened following the Hanga eruption in 22. This was a major eruption involving water, which makes things usually more explosive when there is an eruption in shallow water, and it produced a plume that went up to 57 kilometers. So the reason why we study volcanic activity is not only because there's about 1 billion people living near active volcanoes around the world, which is a big number, to be honest, but it's also because volcano erupting somewhere in Tonga can have a global impact to some extent. And that happens in many ways. Part of it can happen through the ash itself, impacting a wide area as it falls down on the ground. It can also be through the gases actually transported. Especially the SO2 being transported can have an impact when it makes it to the stratosphere. The residence time can be up to a few years. So it can lead to changes of global temperatures for the largest eruptions that make it in the stratosphere. Interestingly, many of the historical events that depict in the history years without summers and terrible famines and things like that, and many declines of civilization have now been linked to eruptions. So just so you know, it is actually something that impacts all ways of life and has impacted our civilization many times. One of the primary control on how high a column goes is essentially through what we call the mass eruption rate, or MER. Here on the left, you see that the plume height that is reached in kilometers somewhat scales with the power law with the mass eruption rate. So this is of importance, of course, for us to understand when something happens very fast. We can tell what is the mass eruption rate. This is one of the things we're trying to do as fast as possible so that we can then inform the aviation industry as to what is the potential for ash dispersion, for instance, if they have to divert routes and etc. It's also important, like I said, for SO2 to understand how far is the ash and gases moving and how long they will stay there. And all of this is basically a collaboration between climate scientists and volcanologists, right? Now, these are impacts of plumes going up, right, becoming buoyant. But there is another aspect of that captures a lot of my work, and that captures a lot of my colleagues' work, is when these plumes aren't buoyant anymore. When they aren't buoyant, they are negatively buoyant, right? So they are denser than the atmosphere. That means that the mixture density between the hot gas and the solid is denser than air, right? Which basically is a result of lack of entrainment. There is not enough entrainment to dilute and warm up the air that is entrained so that it collapses and form pyroclastic density currents, more informally known as pyroclastic flows. So those are mixtures that are really hot and they go on the ground, and they've led to catastrophic events in the past. If we just look at some of the events of the last century, it started with the French island of Martinique. 30,000 people died within a few minutes. It's like a nuclear blast, but it is volcanic in origin. In Montserrat happened again, but we knew a lot more. So we managed to evacuate. I mean, my colleagues managed to evacuate a lot of people, and only a few hundreds of people were affected there. But unfortunately, some events are much more difficult to predict. And in Guatemala in 2018, over 1,000 people died again from pyroclastic density currents. So a lot of the work I do is really trying to understand how do we prevent these kind of disasters. They are human disasters in many ways, So, but I take it from the physics point of view of how do we predict the behavior of the hazard itself. I want to show you an example of what a background volcano activity can look like, and it illustrates the range of things we're dealing with in terms of fluid mechanics. You have magma that's pressurized here, and that will blow a plug somewhat. As it blows the plug, it fragments this mixture into a wide range of grain sizes, from very fine ash that is well coupled to the hot gas, and you can see rising up, to coarser ash that can settle out in the tephra plume, and some of the blocks you've seen even earlier going around the drone. If we come back, you will see all these very large blocks moving as ballistics. So they are rapidly accelerated by this pressure gradient and drag, and then really rapidly decouple from the mixture, essentially, and travel as ballistics. Now, this was the background activity of Fuego volcano. Unfortunately, Fuego volcano also does eruptions that look like this one that happened on March 10th. A much larger erupted volume creates much larger columns, right, as I mentioned earlier. But because of the type of magma, the relatively low viscosity in this case that is involved, there's not lots of fragmentation happening. And a lot of the magma ends up creating large blocks that pile up on the upper slopes of the volcano. During that event and during the former events of the last 10 years, including the 2018 June 3rd eruption, the upper part of the volcano ends up collapsing this hot mixture of rocks that transforms into a Parkless density current. It's essentially like a rockfall. So a lot of this comes down to trying to understand the dynamics of the plume in the first place, and the partitioning of all the different sizes involved, and the gas itself, whether it goes up or down is essentially the question here. I just want to illustrate why Guatemala, at least personally, has really been a driver of my research that has been achieved thanks to ARCHER2. We have, in this case, the upper part of the volcano collapsing. It is a tiny volume compared to landslides we can observe in mountains and all, but it is a few times more mobile in terms of when you scale it by volume and the slopes involved than any other rock fall on Earth. The reason is that the mixture is volcanic and hot and brittle and able to fragment during transport. So you form a lot of ash, and that mixture is then propagating within this sinuous valley, and in some cases filling the valley and overbanking, as it did in 2018. This is a map on the right showing the event started here in blue, moved down in the valley. Part of it went into the southern valley and the other part in the northern, called Las Lajas. And then it went down slowly, at a pace that is about 10 to 15 meters per second, went down slowly there, and eventually filled up the valley very rapidly. As it filled up the valley, the last pulse of that collapsed scar, when it arrived, essentially didn't have much of a valley to move on and overflowed towards the village. The reason why people live there is that there was a civil war in Guatemala, and people have been placed there because they're all from communities, indigenous communities. So it's a cheap land that the government put these people there. And unfortunately, they were put there the year prior to the awakening of that volcano after decades without any activity. So there was not much history, about these events or these kind of possibilities. So what brings me here today is to talk about MFIX, which is a Department of Energy 3D multi-phase flow solver that I have been adapting in the last many years to study paraclastic density currents, plumes, and in general geophysical flows. Essentially, it solves the mass continuity equation, right? The momentum equation of the different solid and gas phases and the interaction between them. The coupling is done through pressure and drag forces, as well as between solid phases through the stress tensor. We use the kinetic theory and over friction, basically terms, that is built already within MFIX. Many of the additions we've made so that we can simulate volcanic eruptions are in the energy equation. MFIX was essentially done to simulate fluidized beds, so it's much more concentrated. But when you have volcanoes, you have very complex and wide ranges of interactions happening, especially with the atmosphere, where you have very large pressure gradients happening as the mixture goes up. So we added a couple of terms, and we also added large eddy simulation, which was not necessary for fluidized beds, hence due to their high concentration. So what brings me here today is that I proposed that image 6 or 9 months ago, I don't know, which illustrates a simulation done with MFIX, which was the first of a kind with MFIX, where we used, using ERA5, the atmospheric information of the June 3rd, 2018 event, which started as I'm depicting here, with a plume. For a few hours, a plume was formed and moved up to 15 kilometers in the atmosphere. part of that plume obviously is made of a wide grain size. Even though fragmentation was quite efficient in that case, it wasn't efficient enough to only make ash. A lot of the blocks piled up very proximally. Here's an example of this seen as a video. What I'm illustrating here is a rendered simulation of the actual topography upon which my 3D simulation is running. I'm injecting this hot gas particle mixture within a conduit at the top of Fuego, and we have the atmospheric condition of that day. So we essentially have 2D wind fields, but because the topography is there, we essentially have a 3D wind field. And we also include not only the pressure gradient, we solve the equation of state for the atmosphere. So we also include the effect of the atmospheric humidity as well. So this was the first of its kind and enabled really by ARCHER2, because with about 1,000 to 2,000 cores, this only takes a few days to run. So this was really fun to do. And it was really important for me to be able to do so. Just so you know, I lead this research group, the Complex Geophysical Flow Lab. I'm an ARC fellow that just passed my 10-year review. And in my research group, we study both discrete element methods to understand rheology of granular mechanics in industry, but especially in the environment, including around volcanoes. I also supervise people in the US where we work on granular mechanics and plumes. The thing that I want to say is that this simulation was the seed for a bigger project. And this is the one that we just got funded through the NERC UKRI funding scheme, where the Pushing the Frontier is about £1 million funding us to study complex plume dynamics in order to understand the effect of complex wind fields and atmospheric profiles, as well as complex sources. When very large eruptions occur, and I can play this video just to show an example of complex wind fields. When very large eruptions occur, the source is not a circle anymore. It may take the shape of a ring or much more complex, and etc. So we wanted to study this, as we know that there's many volcanoes on the planet that can create this kind of activity, including the one that is somewhat closer to the UK, which is in Campi Flegrei near Napoli. So I need to finish now, but I just want to say that I also simulate things at much smaller scale. This was a simulation also done with ARCHER2, where we benchmark our simulations against small-scale experiments, which basically is a saline particle-laden heated flow. We can, at the lab scale, reproduce the dynamics of volcanic plumes quite well. The bulk dynamics, not the microphysics, obviously. And I will just leave you with a cool video that shows you that partitioning I mentioned, right? Depending on the color you look at, some of the mixture is going rather up, or the dark red and orange is actually going to feed a paraclastic density current going down that valley here. And this is in Santiaguito in Guatemala as well. All right, thank you everyone for your time. Happy to take questions.
Thank you very much, Eric, for a very interesting talk. Is anyone online has any questions in the chat? Otherwise, I've got a couple. Okay, so with your new project and the additional complexity you're looking to model, have you got an understanding of how that's going to change the type of simulation and the scale of simulation you're going to be looking at?
So just to clarify, so we'll do a lot of with that new project. So you mean the one we just got funded?
Yes.
Yeah, so the project starts this way. It's essentially trying to parameterize the entrainment within complex plumes, the effect of wind, like shear, essentially, as well as the complex shapes. Because all the very rapid models we have, those 3D models are fast, but they're not fast enough to be useful in operational hazard assessment, are 1D. And in a 1D model, they're integral models, which work very well when you have simple geometries and atmosphere. We have a parameter which is essentially the air entrainment. It has a huge control on how high the plume goes, as you can imagine. At the vent, the density of the mixture is much higher than air, and then can become much lower, and etc. Right, as it entrains. So what we will do is simulate natural events and experiments, and we will calculate entrainment, make it a parameter that we can be a function of the Richardson number and the geometry. And then we'll include this in 1D models that I use in NAME to predict the ash dispersion, which eventually feeds into the VAX, the Volcanic Ash Aviation Advisory around the world, that's advising the aviation industry to divert flights and etc. So that is kind of the how we move from simulations onto something that is applicable for operation hazard assessment.
Excellent, thank you very much. I think Sebastian has one question in the chat. It says, what led you to choose MFIX in the first place?
There are other models that could be quite useful. I'm starting to use also one that is on OpenFOAM. MFIX, it somewhat links to the fact that when I was in New Zealand doing my PhD, I then moved to the US at Georgia Tech, and my advisor had started with MFIX, and I really wanted to study granular rheology. It had a GUI, one of the few DEM codes that is open source and has a GUI. So I started there, and then over the years, I started adding more and more things, but on the continuum side. So I think it is, I see this as like for me, for my career, it was really useful, but I think as a future, I will build on a second version of MFIX that is being built for the last 5 years, MFIX EXA, which will allow us to do exascale computing as it is leveraging GPU computing. It is 500 to 1,000 times faster than MFIX, but unfortunately it only has so far the DMCFD capabilities. So the large plume simulations and natural scale simulations that cannot be done by resolving every particle cannot be achieved yet, but in the future surely will be. So we would be leveraging GPU, and that would be exciting, I think.
Fantastic. Thank you very much for your time today. So in the interest of time, we'll move on to our final speakers. So to finish off, we have a double act of Sebastian and Rui from APTC. So I'll let you two take this away.
Hi, thank you very much. This is Rui speaking. I'll start. This is work that I did during my postdoc at the School of Chemistry of Edinburgh. And so there are a few people that I need to acknowledge for a lot of contribution to the work done here. First and foremost, Infinium UK, they funded this entire collaboration. My supervisor, Professor Philip Camp, that guided most of this project. Julian Sint from EPCC, he's the one that gave us the opportunity to run some of these simulations on ARCHER2 and helped with the initial benchmarks and then monitoring all the simulations at the time. And then Alexander Armstrong, who did the vast majority of the experimental work that we compared our simulations to. So I'm going to be talking to you about GMO and simulations of GMO. So just a quick primer, what is GMO? GMO is a surfactant that is a molecule that has a polar head. So on the image on the top right, the head is the bit on the right with all the oxygens. So that has a little bit of charge. And then neutral tail that kind of likes things more oil, where it has the head like water, molecules with charge. In an oil, which is the main objective of this project was to simulate GMO in an engine-like environment and then do the experiments in the same kind of environment. The tails like to face the oil. So whenever there's any kind of water contamination in the oil, what will happen is the GMO will form tiny reverse micelles around the water droplets. So the image on the top left, what you'll see is a tiny water droplet and then the GMO wrapping around with the tails facing the oil. The oil is not shown. Near a surface, and in particular here would be interesting in looking into iron oxide surfaces or steel in an engine. It was the common belief that the GMO and most other charged surfactants would form monolayers on the surface. So with all the charged heads on the charged oxygen and iron atoms on the surface, and then that the tails would in an orderly fashion point all inwards towards the oil. And whenever any impurities, especially like water, would happen, then that hemimicelles or half micelles would form around those impurities that would be attached to the wall. The reverse micelle in solution, so the top left, that is very well defined, very well studied. The other ones are more speculations because it still is really hard to do analysis or experimental analysis of these kind of systems next to surfaces. So in solution, you can do stuff like X-ray diffraction or neutron reflectometry. Near the surface is a lot harder to do, and only recently the methods have been developed to study this in depth. So when the case that it is hard to do experiments, we tend to turn into simulations or into computational experiments, and that's what we had done. Here I'm showing a bunch of different systems with different concentrations of GMO, and with or without water. So at the bottom, the three systems at the bottom have water, and the three systems at the top do not. It's just oil and heptane if you're interested. And then from left to right, we are decreasing the concentration of GMO. And what we actually see in these systems is that we kind of had the picture the wrong way around. What we see is micelles adhering to the surface on the dry oil, and on the one with water, what we see is a very thin layer of water across the entirety of the surface, the iron oxide surface, and then we see a kind of monolayer of GMO pointed inwards, especially on higher concentrations of GMO. So the image is D and E. D has quite a high concentration, so we still see, if you can see on the middle of that image there, you can see a little bit of a micelle forming on top of the monolayer. So this led us to, this was basically the beginning of the project, and see if we could actually do some experiments on this and compare the simulations and the experiments, and learn something new, because something about our model was wrong into how these systems form and behave. So the first step after that was try to simulate self-assembly of GMO in solution. No surfaces, just GMO, oil, with and without water, and see what kind of sizes of micelles, because these experiments had been done decades before, experimental, so the size of the molecules are well known. So we could compare the sizes of our simulated molecules compared with the experimental values and see if they match. Because if we're seeing that the micelles that we are forming were wildly different, then our computational model was wrong. We need to check all our parameters, the charges that we were giving to each atom, and all of the force fields and all of that. However, the most common way of doing this is to just put in a couple dozen of molecules in a small box and let it run for a while, because self-assembly tends to take a very long time in molecular dynamics time. So it's not easy to do very large simulations of these, at least not with the systems that we had access to beforehand, our tiny group cluster with 40 or 50 cores. So with ARCHER2, what we were able to do is to scale up this simulation on a way that we had never done before. So before that, I was doing maybe 100,000 atom simulations if I was lucky, and at this point in ARCHER2, we were able to run a 2 million atom simulation that simulated 51 nanoseconds of time. That is more than double the average time for micelle formation to happen. So what we were able to do here was to calculate kinetics of the formation of micelles and have statistics on the size of micelles, and we could compare that to experimental values and validate that our computational model was giving us good results in solution, and the surfaces had been validated previously, so we were fairly confident that our simulation on the surface was correct. So what we did then was we got in touch into the people at ISIS, Alexander Armstrong in particular. He ran a series of experiments on their neutron reflectivity apparatus, and we developed a method to improve the output of our simulation that better compare with the density profiles that they get from the neutron reflectivity experiments. I won't go into detail about these graphs. I just want to point out, especially the ones on the right, that the top one was before we developed our model. The solid lines are the simulation, and the dashed lines are the fit from the experiment. And what we see there was that the model was very rough. It was too much atomic. We're simulating very smooth surfaces where real surfaces are not smooth. So once we introduced that roughness into the simulations, we were able to get fits that were much closer to this, or simulations that were much closer to the fits from the experiments. Finally, for me, just to acknowledge that this project, this work was part of a larger project that last week was awarded with the ISIS Impact Recognition Awards and that is Peter Dowding that went into to receive that award.
Cool. So yeah, I will take over. So basically, for that visualization, we did all of the, and his team did all of the scientific work, and I just took the data. I mean, he gave me the data, I don't took it, and make something that tried to look nicer. Basically, the idea was to make it something more appealing for a wider audience, more visually pleasing than something too scientific and only targeted to scientists and to peers. So that's what I try to do with that. And so how to do that? There's several things. Try to basically pick harmonious colors and materials for the different particles. Try to make it more visually pleasing. It's not a science. It's more of a trial and error process. Select a relevant viewpoint for where to put the camera, the virtual camera in the domain. Basically, I'm saying all of this now, but in the next few slides, I will show you the process. And finally, I think one of the main difference compared to more scientific visualization targeted to scientists is to use something like Blender here for ray trace rendering, which basically means you add some physically accurate optical process in the visualization, which makes it more tangible, and you can play with light more. You can tweak a lot more of the end results of the visualization itself. You have access to a lot more setting the parameter of the camera or the lights or anything. So basically, what Hui gave me was the data points, so like the physical locations of all of the particles in one of his simulation at one time step. So it was in the middle of the simulation. That plus the diameter of the particles and the type of particle they all was. So when you load everything to Blender, you can come up with something like that. Here, there's no different color for different things. It's just everything is white, and I have a couple of lights set up and everything. Once you color everything with the actual particles, one interesting point is that here we want to put some meaning into the colors themselves. For example, here oxygen, there's two different colors for oxygen, and we have one if the oxygen belongs to the micelle, that it was?
Surfactant.
Surfactant, yes. And one if the oxygen belongs to water. So like you have the H2O particles that are really visible because also they're blue, and so that they really stand out, and you can clearly see them. And the same oxygen will be red if they are part of the surfactants. And so that, sorry, I'm showing with my cursor, but you don't see that. So but yeah, you can see oxygen is the same particles as two different colors. And same thing for hydrogen, either light blue or purple, because they are belonging to two different things. Species. You can tell them more on the visual side and not on the molecular dynamic side. So the second point was also to pick a location, like a placement of the camera where you could visualize that clearly enough. So we picked a place where you could see the water droplets and you could see the micelles, things around it. The next thing to do was to add sort of a fog, in a sense, in Blender. Yeah, it's like a volumetric object, just so that you separate more what's close to you and what's farther away. It's not here to replicate what the oil would look like or anything like that. It's more here to have a bit more, so visually it's a bit less crowded, and all the other particles are still there in the background, but you see them a lot less, and it makes it the thing that are closer to you stand out a lot more, and you have this sense of depth and sense of distance a lot better as well. And that's also emphasized as well with where the light sources are. There's like especially light source again, pointing with my mouse, that doesn't help. There's again a light source in the blue, in the thing on the top left-ish over there, and that helps seeing that distance as well. One other thing as well is quiz simulation, where periodic in terms of, so a simulated box, a 3D cube, but yeah, all the sides were periodic, so it was sort of infinitely large. When you look at the domain here, it was a side of the domain, and that's something I did not notice before. Is basically you have some particles that are like floating in the air, in the ether, let's say, in the oil. So some particles are floating, and there should be like there's never a single particle of hydrogen here floating. And it was just because I was on the side of that box, and in reality it was like it was replicated. So when you actually account for that periodicity, you have a lot more things, a lot more particles, and so that's what I did also in Blender, to basically replicate the original box in different directions a couple of times, so that first you see a lot more depth. So in the distance at the top left corner here, you see like particles and things a lot further away as well, and you have more particles towards you, and you have now the full length of the
surfactant,
the black part and black and purple part. You have the full length of that, and you have basically it's just physically accurate now and didn't used to be. So that's one of the key points, is when I do visualization on fields I'm not too aware of, I make sure I have someone that knows what it should look like, so that this kind of mistakes can be picked up early on. I think that's pretty much it. That's the final visualization that we submitted. And that looks like. Thanks, everyone. And if you have any question, I or Hui would be happy to answer. Probably Hui more than me, but
no, I might be asking about ray tracing in Blender, and
true.
Not me.
Yeah, I can see my accent is quite very easy.
It's potted miles away.
Yeah.
Okay, thank you very much both. I don't see any questions in the chat, so a question around the simulation for Ruri, I suppose. Sort of, what were the sort of run parameters? What were the timescales to produce this simulation?
What were the what? Sorry.
What were the sort of like job parameters for the simulation to produce the results? The
big simulation. So in terms of atoms, 2 million atoms, 51 nanoseconds at 2 femtosecond time step. So I don't want to do the math, but 25 million time steps from the top of my head. If my math is okay, it might not be. And almost a terabyte of data outputted. So coordinates every picosecond, or every couple picoseconds, I can't remember right now. So that the positions of the micelles and the size of the micelles could then be calculated and averaged. Is that the parameters you were looking after?
Yeah, that's great. Okay, I think that's a question for data in the chat. Are you guys able to read that, or do you want me to read it out to you?
It's me. How much of the process for creating the visualization Blender is my process for automatic pipeline? So in this case, because it was only for a single frame, I didn't animate it, I didn't make a movie or anything like that. Everything was really a manual process. Because I don't really need to automate anything, and so it's also for me the first time looking at this kind of data, looking at this kind of the type of file and everything. So I was also just figuring out as I went. The moment you want to try, if you want to do like an animation or load several times step and do animation and all of that, you need to automate everything, because you don't want to have any manual interaction. So if you want to run the 500 time steps or 500 frames, you don't want that to be manual. So the thing that will be always manual will be the setting of the scene, so where the camera is, where the lights are, what kind of color you have for every single atom. All of these parameters, like the density of the fog, in a sense, all of that will be a manual thing and will be tweaking based on what looks nice or what looks good or what you want to achieve. Everything else, like the loading of the data and the pipeline, once you have that set up, all the pipeline, yeah, if you want to animate, it needs to be automated. So basically loading the data and doing all the processing on that if there is any that needs to be done, needs to be automated. If you had a new time step, I would need to redo all the things manually because I did a lot of things manually last time. But now that I know what I'm doing a bit more, it will be a lot faster.
Yeah, if the intent was to create a movie from all the time steps, with that in mind, you'd be able to just set everything once and then just run all the time steps through a pipeline.
Yeah.
What would you expect to see? Is there something scientifically interesting if you were to try and produce a video from this?
So I did do a video with my kind of render. So if we go back several slides, very different level of quality, but we did create a video to see the formation of the micelles. It is one of the supplementary information on the paper that we published. The citations on the acknowledgement slide. It is useful for us on the first stage to see if there's nothing weird going on in the simulation. So it's a very good way to see that, the charges that you set for oxygens are wrong because they're all repelling everything, for example. But then to estimate a quick estimation of micelle size, micelle numbers is very easy to do from a movie rather than from just the raw data. And then to share around with our industrial partners that are not necessarily experts in molecular dynamics, they're experts in producing these kind of components and developing them rather than studying them. It's much more easy way to understand what's happening in simulation, and especially in surfaces where we were much more near the edge of knowledge rather than solutions that are much more well known.
Excellent. Thank you very much for a very interesting talk, both of you. And thanks to the rest of our speakers for joining us today to provide a variety of different topics for us to discuss. Our next webinar will be around one of our ECSE projects on the 9th of April. And thanks to everyone again today for joining and attending this webinar.
Thank you.
Thanks a lot for the opportunity.
Yeah, thanks.
Bye.
Bye, everyone.